Good. So, welcome back. I'm going to say a few words about what are knots and then tell you about the Jones polynomial. So, it's kind of embarrassing that you know, in the topic that I am teaching about, I kind of strongly dislike theorem number 1. Here it is, theorem number 1. Let me explain what it says and tell you why I dislike it. So, first of all, well, it's a reduction of knots and links, of the theory of knots and links, essentially to combinatorics. So from topology to combinatorics. Diagrams modulus on relations. So first of all, what's the topology side? So let's define knots and links. So the definition is a bit more intricate than you would think. So your intuitive definition, your first attempt at the definition would be that this is continuous maps from S1 into, I don't know, maybe R3 that are injective. So I'll just denote it by making it look like an inclusion sign. And modulo deformations of such, so homotopies of such. Namely, well, just deformations in which you always deform within the class of embeddings of S1 into R3. Well, this would be a knot, and if I wanted to include links, so links are just knots with several components, I would have to make it a disjoint union over k copies of S1. That's a lovely definition, except it's wrong. So, for example, or I don't know if it's wrong, it's a good definition. Definitions cannot be wrong, right? So, but it doesn't give you the results you want. So, for example, here is a trefoil knot. Okay, namely the knot is really the shoelace along with my hands and my body, right, to complete it into a circle. Okay, so here is a homotopy that turns it into a trivial knot. Whoops. So you see, well, with a physical object like a shoelace, there is still a tiny thing here. Okay, but if this really was an S1, so, you know, if this really was a zero width thread, I could just pull until this little bulk here becomes a single point, and then it's just not there. And that's a completely continuous process. So, in fact, knots are not defined within the continuous world, or are not knotted within the continuous world. So, you can change it to either smooth or piecewise linear, or there are several other approaches. And that's all I wanted to say about it. That's a reasonable, well, a warning. Okay, it's just not about continuity. It's about something slightly more intricate. Okay, then comes the second point, which is that knots can be represented by knot or link diagrams. So what are knot or link diagrams? These are pictures like the pictures I've shown last time and like I've drawn, basically picture like this. So this is a picture in the plane, So each such picture clearly represents a knot, and with some effort, you can show that whenever you have a smooth map, you can find the direction so that if you project from that direction, you have only finitely many crossings. So maybe the picture will not look so smooth, but a bit more rugged, but still you'd get a link diagram. Okay? And then you can spend even more effort and use, in the case of, if you're defining knots and links using smooth maps, you'd have to use the, what is it called? The Tubular Lemma, the Tubular Neighborhood Lemma, to show that if you deform the knot, you can always, you can decompose the deformation into finitely many steps inside each of which it deforms within a tubular neighborhood of some fixed embedding. And then within each tubular neighborhood you could sort of, well, work a little bit more gently. And then you'll find that the projection undergoes only finitely many changes as you deform from one knot to the other, and the finitely many changes are these. Okay? Either a kink disappears, or a pair of crossings adjacent to each other cancel each other, basically a move like this, or you have one crossing and underneath it a third strand, and you slide it up underneath from below to up. And of course the words below and up are silly, I mean in some direction. It's a lot of technical work to prove this, and it's a bit unsatisfying at the end, because it's a lot of technical work, and it's not about the main problem. It's not about the main issues. So I'll skip it, as I always do. I never go through this theorem. In fact, I so much dislike this theorem that I almost want to change its status from a theorem to a definition. So definition, well, this gets scratched, and instead knot and links are knot or link diagrams modulo these moves. Okay? So that's what they are for us. I think I'd like to make another comment. So, strictly speaking, as stated, the word knot or link diagram is still a bit topological, right? Because, well, it's a diagram in the plane, okay? And diagram in the planes are actually a complicated thing. I mean, in fact, you know, even circles in the plane are a complicated thing, right? So, here is a circle in the plane, and the Jordan curve theorem says that it separates the plane into two parts, and that each of these parts is itself homeomorphic to a disk. But it's a hard theorem, okay? So, so this isn't yet combinatorics, okay? Or algebra, okay? But on the other hand, I can turn it into algebra relatively easily. And again, the proof of the statement that a a link diagram is equivalent to this combinatorial thing that I'm going to describe is actually messy and long, because you would need to deal with multiple instances of the Jordan curve theorem. And again, it's a complete waste of time, and I'm not going to show this book. Anyway, let's turn this into combinatorics. So what is a knot or a link diagram? So, you know, you can say this is either a theorem or a definition. I like it depending on your mood, okay? So what is it? So it's a quadrivalent graph. Quadrivalent graph, subject to a number of provisions and with extra bits of information. Why quadrivalent graph? Because the vertices are the crossings. So I'm thinking of it as, well, the graph you see here when you project. So the vertices are the crossings, and each crossing is a vertex of valency 4, right? Because 4 edges emanate from each crossing. Okay? Now, what do I have to say about this graph? So lots of provisions and extra information. So first of all, usually in the standard definition of graph in graph theory, you do not allow multiple edges between vertices. So if you have 2 vertices, either there is an edge between them or not. But here, like between this vertex and that vertex, there are 2 edges. So strictly speaking, I should, not just strictly speaking, I should change this to multigraph. So I think a multigraph is the name for that thing where you allow more than one edge between 2 vertices. Okay. Second, and I think this also includes pictures like this where you have an edge going from a vertex to itself. And if not, if the standard definition doesn't allow that, let's declare that we do. Okay? The next point is, maybe I should have mentioned, I always think of oriented oriented edges. So I should have said oriented. And oriented means, well, just that all the edges are oriented. Okay? Then I need, so some information that comes from the plane. So what's the information that comes from the plane? So you can always go counterclockwise around a crossing. Okay? And if you go counterclockwise around the crossing, it gives you a cyclic ordering of the edges emanating from that crossing. So 1, 2, 3, 4, but it's only a cyclic ordering because, well, if you rotate it by 90 degrees, you get a different numbering. Okay, so let me just say it this way. So vertices, which, by the way, maybe from this point on, I will be calling them crossings, are cyclically, or have a cyclic ordering of the edges emanating from them. Let me short it to saying are cyclically ordered, or carry a cyclic ordering, I don't know. Carry cyclic ordering. Okay. 2. So you see, the orientations must match. So if you come into a vertex and then you go to the opposite edge, the opposite edge is now well defined because all you have to do is to go twice using the cyclic order. Right? Go to the next one and then to the next one. So it should be oriented the same way. I don't know how to say, opposite edges on the same vertex or crossing are oriented consistently let me continue here. 3. So you see, in every crossing, one of the pairs of opposite edges is considered above the other. So therefore, it's not just a quadrivalent oriented multigraph with these properties, but it's a labeled quadrivalent oriented multigraph, where the labeling is which pair is above which other pair. Okay? So there is a further annotation. The graph is annotated with over-under information, and what this just means is at each vertex, one pair of opposite edges is called over. Okay? And property number 4. So if you're talking about a knot, when you traverse the graph, namely, when you start at some point and you just go, and every time you get to a vertex, you go to the opposite edge and keep walking, you traverse the whole graph at once with a single pass. Namely, it's a circle. Okay? So, how should I say that? Traversing the graph I think I said it and I don't want to say it again, gives a single path. This is, if this is a knot, or multiple paths. If it's a two-component link, it's going to do two paths, and so on. Okay? And then there is the last property. Well, what I didn't say it is that this graph is planar. Okay? The graph is planar. Okay? So I want to make a comment about what does it mean to be a planar graph. I mean, because this doesn't look like combinatorics anymore. Okay? Right? This means that I can embed it in the plane, but if I embed it in the plane, the question is, how do I embed the edges? And then everything becomes the exact same mess with the Jordan curve theorem and all that, with embeddings that are messy. Okay? So what does planar mean? So planar in this particular context is extremely simple. Namely, you see, suppose you have such a graph. Well, it's obviously planar because I drew it in the plane. But suppose I didn't know it was planar. How do I check if it's planar? So I can check if it's planar. So there is Euler's theorem. Euler's theorem says that if you have a planar graph, so in a planar graph, the number of vertices minus the number of edges plus the number of faces is equal to 2? I believe so, 2. Right? So what's a face? A face is one of those things. But you see, I can tell what are the faces simply by looking at the graph. I don't need to know the thing inside. Okay, I don't need to know about the parts of the plane that are inside. Namely, I start walking to the left of one of the edges, and then every time I get to a vertex, I turn left. The word turn left has a meaning because this meaning is embedded in the fact that the vertices are cyclically ordered. Namely, I follow the, wait, actually left means clockwise with respect to the ordering. So I use the inverse ordering. Okay? So I turn left here, I turn left here. When I come back, I went around one face. Then I start here, and again I turn left everywhere, and that defines the other face. So basically, the faces are defined from the structure we already have. Okay? So planar just means satisfy this equality. Okay? In fact, let's test it. So the trefoil, for the trefoil, we will have 1, 2, 3, 4, 5 faces. So this would be 5. The number of edges is 1, 2, 3, 4, 5, 6. 6. The number of vertices is 3. There are 3 crossing. So 3 minus 6 plus 5 is indeed 2, and we checked. Okay? So that was one. Okay, so now everything is completely combinatorial. There's no algebra in the business at all. Okay? One minor comment is that I slightly lied, because you need to also allow the unknown. The unknown is a graph with no vertices. So make an exception for that. And second, oh wait, sorry, one more comment. I mean, the relations are also defined within that language. So basically, if you have a vertex with a kink, so with an edge that connects to it twice, you can remove it. If you have a pair of vertices that are connected twice and the senses of the which one is over and which one is under are as shown here, you can remove them. And likewise here. You can state it in graph theoretic terms. You don't need the drawing, the plane. So now it's completely combinatorics. And as a complete aside, which at the moment is completely irrelevant and the value of it is completely unclear, but later this will be valuable, you see, since everything makes sense, in fact, without the statement of planarity, you can drop planarity. And then what you will be talking about will not be knots anymore. But it will still be something. And that something is called, so if you drop that, so drop and get so-called virtual knots, or V-knots. So just graphs with all this information as if it was knots, but without the condition of planarity. So V minus E plus F does not need to be 2. Okay. Questions, comments? Yes?
I'm confused by the cyclic ordering part. I feel like each vertex should appear twice in the ordering somehow.
I don't know. So the ordering is not an ordering on the vertices. The ordering is an ordering of the edges. So if you of the edges around each vertex. So if you have a vertex,
Okay.
the ordering is 1, 2, 3, 4. But this order is equivalent to the order 1, 2, 3, 4. So it's a cyclic order. It's not a genuine linear order.
This is just like an orientation of where the knots are relative to each other.
Where the edges are.
Right.
Basically, it's a, well, I don't know if I could probably define a cyclic order. It's a next operation. So for every edge near a vertex connected to a single vertex, there is a notion of a next edge, and this next operation is of order 4. So after you do next 4 times, you come back to where you were. Okay? Good. Okay, so now we know what are knots. That just became a definition. Okay? So in practice, I will never refer back to this definition. I will just use the intuition that we have. Planar thing, planar pictures, modulus these relations. But I just wanted to emphasize that it can be reduced into complete combinatorics. Good. So now I need knot invariant. So what would be a knot invariant? It's a quantity that you can compute from a graph like this, and which does not change when you do any of those moves. And I want to start with perhaps the most famous, with the Jones polynomial. Okay? And maybe before I erase this, I should say that you should please register to this class if you can. Basically, the School of Graduate Studies is putting pressure on the department to have non-empty classes. And if nobody registers, then we have an empty class, and that's bad. Okay, so now the Jones polynomial. So, or in fact, I'll start by defining the so-called Kauffman bracket. And the definition is extremely short, but it's kind of ad hoc. And hence, it was only discovered in the 1980s, even though people were studying knots for at least 100 years before that. So, what's the definition? So, well, I'll lie a little bit, but you'll see. So, basically, it's a map called the bracket, and it's a map from planar diagrams of links. So from planar diagrams of links to, at first, it will be polynomials in 3 variables, but later we will see that it reduces, that it's not really 3. It goes down to 1. So these are polynomials in variables a, b, and d with coefficients in z, with coefficients in the integers. So it's defined by 2 rules. So the bracket of a crossing is equal to a times the bracket of this plus b times the bracket of that. So I have to explain what the notation means. So first of all, this isn't the planar diagram of a link, right? The planar diagram of a link will be a bigger diagram. Okay, this is, but what is written here is a so-called skein relation. A skein relation. And in a skein relation, what we mean when we draw partial pictures is that all partial pictures are to be completed to full pictures in the same way. In other words, for example, you could complete it to the planar diagram of a link by adding 2 caps, right? And then what I mean is that you will be adding them in the same way in all pieces that appear within this equation. I could have completed them, okay, so this is an actual relation. Before it was a relation template, and now it's an actual relation. But the template corresponds to many other relations, because I could have completed those 3 things to a link in other ways. I could have completed it by connecting this to this and this to that. And then I would mean that you do the same in all pictures and so on. Okay? So really it's not a single relation, it's a template for many, many, many relations. So that's relation number 1. Now, with this relation, so suppose you have a bracket, suppose you have a function like this, it allows you to reduce every diagram that has a crossing in it to a diagram that has 1 crossing less, because the 2 things on the right have 1 less crossing. So if you do it iteratively, you end up with a diagram with no crossings. So the second relation is that if you have a diagram with no crossing, well, if it has no crossing, then it just has a number of cycles. Maybe they're nested. Okay? And then the rule is that if you have k circles, you'll map this, the bracket of that is d to the power k. Okay? Or I could say it in a different manner. I could say that if you have a circle and then more, so a circle and then the rest of the diagram, then the bracket, so the circle factors out and gives a factor of d. So the bracket of that is d times the bracket of uppercase d. Oops, sorry for the name clash. And then the bracket of the empty set is 1. Right? And this definition is equivalent to that one. Oh, and I should have said one more thing, one further thing. So you see, what's the difference between this picture and that picture? I mean, rotate them by 90 degrees and they're the same. But you see, rotate this by 90 degrees and it's not the same. So, so the difference is, so there is a convention. So basically, if you start from the lower strand and turn right, so if you start from the lower strand and turn right, you get this arc. And if you start from the lower strand coming the other way and turn right, you get that arc. These are the two arcs that appear here. So these are start from level 0. So let's call the lower level 0 and the upper level 1. I'm thinking of it like a highway interchange. So start from level 0 and turn right. Okay? And if you want to see what this means start from level 1 and turn right. If you start from level 1 and turn right, no matter whether you come this way or you come from the other way, you get the two edges that make this. So this is start from 1 and turn right. And this is sometimes called the zero smoothing of a crossing. And this is sometimes called the one smoothing of a crossing. Well, you smooth the crossing and you do it, well, by these rules. And maybe I should say one more thing. You see, this smoothing operation need not respect the orientation of a link. When I said before, that when I gave the definition of a link, I wanted to say, I said that all edges are oriented. Okay, but the smoothings might not be, do not inherit an orientation from the original edges. So, really I should have said that this is planar unoriented, diagram of a link. Okay? Good. Okay, this is clearly a well-defined functional on unoriented link diagrams. Because, you know, if you have a link diagram with any number of crossings, let's say 2, then you are, you resolve this, you smooth this one in the two possible ways, you smooth this one in the two possible ways, you get a total of 4 smoothings. It doesn't matter in which order you do it, because, well, what happens? You're doing things to things that are far away from each other. You're applying a local law to different locations, so it doesn't matter in which order you do it. So this becomes a certain sum of 4 smoothings, each of which is just a union of circles, so each of which is a power of d. So I could actually compute what this comes out to be. Maybe I shouldn't, because, or should I? Yes? Okay, so let's do it, fine. So, let's see. So you know what? Let's, you know what? I think I want to rotate it by 90 degrees for a reason which will be clear in a moment. So let's do this. And now this has two crossings that are left, well, so this one can be smooth 0 or 1, and this one can be smooth 0 or 1, right? So let's write the 0, 0 smoothing, the 0, 1 smoothing, the 1, 0 smoothing, and the 1, 1 smoothing. And clearly this, I chose it so that the 0 on the left corresponds to, the numeral on the left corresponds to the crossing on the left, and the one on the right corresponds to the one on the right. So what's the 0, 0 smoothing? So maybe I'll just first copy the whole thing. Yeah. I'll copy the whole thing. And then the 0 smoothing is you enter from level 0 and turn to the right. So you turn to the right here and you turn to the right here. Okay? And and the 0 smoothing on the right is you enter on the 0 level and you turn to the right. So you get this. So this is the 0, 0 smoothing. In the 0, 1 smoothing, you flip the crossing, the smoothing on the right. So the smoothing on the left stays the same, but the smoothing on the right gets flipped to being that. And you're left with this picture. In the 1, 0 smoothing, you take this and you flip the smoothing on the left. So you have this picture. And in the 1, 1 smoothing, you flip both. So this is one, this is the other, and you get this picture. Okay, are you with me? Now, 0 smoothing gives you A. So you get this one with coefficient A squared, this one with coefficient AB, this one with coefficient BA, which is the same as AB, and this one with coefficient B squared. And I have to sum everything because of the plus written here. And so the overall result is, sorry, what's this plus? I don't know. This should be error. Anyway, so this is A squared D squared plus AB times D. This is a single cycle, each of these. So it's twice AB D plus B squared D squared. So maybe I should have written it like this. A squared plus B squared. Okay? Good. Well, is it an invariant? So the next question is this an invariant? And the right order by which to check the Reidemeister moves turns out to be not what you think. So you start with Reidemeister 2, it's hard. You then do Reidemeister 3, it's easy. And then you do Reidemeister 1, and you have to learn something new. So it's not the order you think. Anyway, let's check Reidemeister 2. So let's compute the bracket of this and compare it with the bracket of that. Are they equal? So let's see, this is equal to, it's kind of a shame that I did this because now it's exactly the same, except different crossings. So anyway, the 0, 0 smoothing is you turn to the right, and then you turn to the, and then now you're on the upper strand, so you have to turn to the left to get the 0, 0 smoothing. So this looks like this, right? With coefficient a squared. Do I have it right? Again, I started at the lower strand, I turned to the right, this is this, and then I start on the lower strand up here and I turn to the right, and this is this. And then the rest is forced. And strictly speaking, I should be putting the bracket symbol around it, but I'm lazy. Okay? Plus, now, AB times, let's flip this one. So it's this picture, plus another AB times, let's flip that one, so you get this picture, plus B squared, and let's flip both. And if you flip both, you get this picture. Okay? Now let's combine these pictures. So you see, this picture has a circle in it. A circle is worth D. No matter how the rest is expanded, you'll always get a factor of D. So let's remove this circle and call it a D. So you'll get this picture with a factor D. D times AB. Okay? And but you also get this picture from here. This is the exact same picture. But now it comes with a squared. And also from here, and it comes with b squared. So plus a squared plus b squared. And then you also get this one, which is just this picture, and it comes with coefficient ab. Now, I want this to always be equal to that. The only way it would happen is if the coefficient of this diagram, which is the same as that, is 1. So the conclusion is that AB must be equal to 1. So I told you a lie. I said it's a polynomial in 3 variables, but in fact 2 of them must satisfy a relation, or else it will not be an invariant. But then this also has to, you see, this smoothing does not even appear on the left-hand side, so the coefficient must be 0. So this must be equal to 0. And so we lose another variable. So the conclusion is B is equal to A inverse. And if B is equal to A inverse, and this is 1, so D plus A inverse plus A to the minus 2 is equal to 0. So D is equal to negative A squared minus A to the negative 2. And things are looking bad, because we lost 2 variables to get invariants under one move. And things are looking bad because it looks like if we wanted invariant under 2 more moves, we would probably lose everything. But then luck hits and we don't lose everything. Okay? So next time I will show you, 1, that R3 is actually trivial. Even though it looks complicated, it's actually trivial. That R1, the missing move, is fun. And 3, I will show you that this can be, remember my last bit of ideology, I want to implement everything. So I will show you that all of this, even though it looks, very non-computer-like, you draw it in the plane and all that, is like 5 lines of code. Okay? Good. So any questions or comments? So please register and see you on Wednesday. And Leonard, you can turn off the video.